Hello everyone, welcome to lecture 43 of the course Diffusion in Solids. Last class we started talking about the grain boundary diffusion, and we looked at what is known as the Fisher model in order to mathematically describe the grain boundary diffusion problem. And we saw that because of the two-dimensional nature of the problem and so on, we saw that the equation becomes fairly complex actually. We even did not go through the derivation because it is a long and tedious one. So, we just wrote the expression, and now you may ask, sir, what do I do with this complex equations? And how do I apply it to my regular research problems and so on. So, now we basically today that is where we want to discuss the classification of this grain boundary diffusion into the kinetic regimes, which basically helps us to understand a little more easily the influence of grain boundary diffusion in relation to or in relative to the lattice diffusion. See, what is most important for us is that at any given temperature, if my material diffusion is happening, how much it is influenced by grain boundary, how much it is influenced by lattice. So, this relative contribution has to be understood carefully in order to determine the grain boundary diffusion coefficients, or in order to understand the diffusion process in the material. So, we will look at some of the useful classification which is known as this kinetic regimes of grain boundary diffusion, and we will also shortly see how to determine the segregation factor which we introduced in the previous lecture. So, when it comes to polycrystals, we know that in polycrystals there is a decent fraction of grain boundaries, and not only that, the grain boundaries fraction can change. For example, you have a grain growth where it was a small grain size initially, it grows to a larger grain size. This happens in the polycrystalline materials. So, therefore, the relative contribution of the grain boundaries can change in polycrystals also as a function of temperature. So, therefore, it is important to understand these grain boundary diffusion contributions specifically in polycrystals, and let us see how do we do that. So, each regime, each kinetic regime prevails in a certain domain of annealing temperatures, annealing times, grain sizes, lattice, and the grain boundary parameters. Okay. So, see, by regime what we mean is again we are trying to classify the regimes so that we understand the relative importance of the grain boundary diffusion relative to the lattice diffusion. Now, this knowledge of diffusion regimes is also important for designing diffusion experiments and for the interpretation of their results, because the shape of the diffusion profile will depend upon the dominating kinetic regime. And the diffusion parameters that can be extracted in different diffusion regimes are different, and therefore, must be identified in the reliable studies. This will become more clear when I introduce to you what actually these kinetic regimes are. So, the most famous classification of the kinetic regimes was what was put forward by Harrison, which classified the diffusion kinetics of grain boundaries in polycrystals into three regimes, which are called A, B, and C. And this was the first one and still the most widely one used for the polycrystals. This is how this classification looks like. So, it is A, B, and C. What you see here, for example, let us say this layer above in the dark blue color, it represents the layer of atoms which is deposited on the surface. And this portion here you see These represents the direct diffusion. So this represents the concentration or the diffusion that has happened because of the or within the grains. Now, within the grains, there are we saw in the last class there are two types of diffusion can occur. One is the direct diffusion. Another is the diffusion coming as a leakage from the grain boundaries. Therefore, you see that as you go towards the end of the grain boundaries, you see this kind of a profiles. So, here there is a flux here, there is a flux here from the neighboring grain boundaries. But you because in the type A regime, you see that you almost have a very constant looking kind of a system. Now, this akinetic regime is observed at a higher temperatures, and B-kinetic regimes, you see that you see some diffusion in lattice, you see some concentration in grain boundaries, whereas in the type C regime you see that there is nothing in the lattice at all, but there is only diffusion present in the grain boundaries. And type A is observed at the highest temperatures, type C is at the lowest temperatures. So, the key takeaway from the schematic, first of all, you should see is that again the relative amount of tracer that is present in the type C regime. When I say relative, it means what is present in the grain boundaries to what is present in grains is different in C regime, then in B regime, then in A regime. So, this is what is the basis of the classification, and now we will try to see one by one these kinetic regimes and what do they mean. So, first of all, let us look at this akinetic regime. Akinetic regime, what happens is that the diffusion along the lattice and diffusion along the grain boundaries is comparable. Okay. So, it is comparable means that you see here that is represented the extent to which diffusion has happened in the lattice as well as extent to which diffusion in the has happened in the grain boundaries are almost similar. This can happen when the diffusion annealing is done at very high temperatures or for very long annealing times, and typically in materials with the smaller grain sizes. So, what you see is that here the fluxes which are the leakage fluxes, here these grain boundary fringes overlap with each other. Means you cannot say, for example, if I take a concentration here, I cannot say that this concentration has come from this grain boundary or this grain boundary, because the grain boundaries are spaced so close. So, here any concentration that I take may have an influence from the neighboring grain boundaries, this neighboring grain boundary, this neighboring grain boundary. It may be coming from the direct diffusion as well. So, here it is not possible to distinguish between the individual concentration contributions of the grain and the grain boundary. So, I take a point here, let us say. I do not know whether this concentration is separately coming from the direct diffusion or from the leakage flux. It is the sum of all. So, in a sense, what I am able to measure is only an effective value. That is why in this akinetic regime, the diffusion coefficient also that you measure is called as an effective diffusion coefficient. You cannot measure a lattice diffusion or a grain boundary diffusion coefficient. So, this basically happens when your grain sizes are very small compared to your diffusion depth. So, root dt is greater than or equal to d by 0.8. This is an empirical relation which is generally found to be applicable when the akinetic regime holds. You see that almost a planar diffusion front is observed with the depth varying as root t. Now, as I said that from a macroscopic point of view, this obeys a fixed law with some effective diffusion coefficient d effective, and these d effective is actually a combination of the grain boundary diffusion coefficient and the lattice diffusion coefficient. So, this d effective is written as g into dgb plus 1 minus g into D, which is known as Hart equation, and G is the fraction of atomic sites in the grain boundary of the polycrystal. So, what you measure here in this type A regime is basically an effective diffusion coefficient. So, you will when you try to measure, when you try to plot log C versus x square for the akinetic regime experiments, you will see a straight line, but that straight line slope will not give individually a lattice diffusion or a grain boundary diffusion. Okay. So, for example, if I plot in the akinetic regime log C versus x square, then what I get is a straight line. But this slope of the straight line does not give me a lattice diffusion coefficient or a grain boundary diffusion coefficient. What it gives me, this D effective. So, this D effective now has a contribution from the grain boundary diffusion coefficient as well as from the lattice diffusion coefficient as expressed by this Hart equation. Now, let us move on to the B kinetic regime. The B kinetic regime is a very interesting one. Here, it happens at the temperatures which are intermediate between A and C. So, these are you can say somewhere midway, not a very high temperature, but not too low a temperature as well. So, as I said that relatively lower temperatures and short annealing times, but not as low as C kinetic regime, and with the sufficiently large grain size. This is observed when your root dt is actually less than d, and it is still greater than your grain boundary diffusion width, grain boundary width delta, which is approximately 0.5 nanometers. That is a widely accepted value. So, remember in the akinetic regime, your root dt was greater than grain size, the d. Here, the root dt is much less than your grain size. What that does is that suppose if I take some point here, suppose if I take a point here, here I can say because the grain boundaries are widely spaced, because the grain size is large enough, the leakage flux of the grain boundaries do not overlap. In other words, we say that the lattice diffusion fringes of the grain boundaries do not overlap. So, whatever suppose if I am here, then this I can say that whatever is here, the contribution is from the leakage flux of this grain boundary. There may be a contribution from the direct diffusion, that is okay, but there can also be a contribution here, and lattice diffusion coefficient or contribution is also limited, remember, because the temperature is not that high. So, here it is possible for me to say that if I am, let us say at this point I am near this grain boundary, then the contribution is coming only from the leakage flux of this grain boundary and not from this grain boundary. Similarly, when I am here, then it is coming from this particular grain boundary. So, the neighboring grain boundaries fringes do not overlap. That is the most important characteristic of this B kinetic regime. And what it does is, it allows us to measure the lattice diffusion separately and the grain boundary diffusion coefficient separately. So, in this particular case, your profile will look something like this. So, you will have a near surface part which represents the slope of which represents the lattice diffusion, and you will have a long tail like this which represents the grain boundary diffusion. So, you see that the first part extends to roughly 3 to 4 times of root dt, and this is like a Gaussian function. And the second is a grain boundary tail, as I said, due to enhanced or simultaneous grain boundary diffusion adjacent to the grains. And this does not follow z square dependence. Okay, so this we will see that it doesn't follow a z square dependence, but in the case of B kinetic regime, because you have two distinct slopes present, you can estimate both the lattice diffusion coefficients as well as the grain boundary diffusion coefficients. So, this grain boundary diffusion tails, by tail I mean is this part, this part here. This part, how long that is, it depends upon the value of the parameter beta, the Leclerc parameter. If the beta is too small, then this gradient in this tail tends to level out. So, this is shown here that if beta is equal to 0, this is almost equal to the case where dGB is equal to d, and the grain boundary diffusion coefficient is not enhanced at all. As the beta increases, the more pronounced the diffusion fringes along the grain boundary become. So, typically if you want to conduct a reliable grain boundary diffusion measurement analysis in this, you want to ensure that the beta is greater than 10. Now, because of the dual nature of the profile, you cannot deduce the dGB directly, but what you can deduce is the quantity known as a triple product, which is a product of S into dGB into delta, and using an expression of this sort for the instantaneous source condition. Remember, it is dependent on the not the slope of z square versus c, but it is c bar versus z to the power 6 by 5. So, in the case of the grain boundary diffusion coefficient, it is the not in the B regime, I mean, here the z to the power 6 by 5 variation is observed. Again, these are more empirical relation than having a real physical meaning. Usually, it is a good idea when people are, although as I said that you can determine the d values from the B kinetic experiments. That means you can determine the lattice as well as the grain boundary diffusion coefficients. In practice, usually it is preferred that you know the lattice diffusion coefficient from separate experiments before, and that you use the value to design your experiments in the B kinetic regime. So, this particular equation is valid when the parameter alpha is less than 1. This alpha is S delta by 2 root dt, and the parameter beta S dGB delta by 2 d root dt must be large enough, that is greater than 10 for this solution to be valid. So, remember, alpha less than 1 and beta should be greater than less than 0.1 and beta should be greater than 10. C kinetic regime is perhaps the easiest to understand. This is the regime which is valid at very low temperatures and very short diffusion annealing times. Here, the entire diffusion takes place only along the grain boundary without any significant leakage into the adjacent grains. So, this is almost like your one-dimensional diffusion, and this occurs when your root dt is much smaller than the grain boundary width itself. So, you can imagine the grain boundary width itself is 0.5 nanometer. That means the lattice diffusion has to be even less than 0.5 nanometers for the C kinetic regime to hold. The solution mathematically is given by exponential minus z square by 4 dGBT, which is a Gaussian solution. This kind of root dt is greater than is less than delta is observed when alpha is much greater than 1. Alpha greater than 10 also proves to be sufficient sometimes. So, remember, alpha is S delta by 2 root dt. So, alpha greater than 1 means that this should be smaller than delta. So, this is a typical profile in the C kinetic regime, where this you see that here the initial part is very less. This is obtained from a sectioning experiment, and here the DGB is obtained by fitting the straight light, and this is the value that is presented here. Now, although the mathematically and physical meaning of the C kinetic regime is easier to understand, the major challenge is that the measurement itself to be performed in C kinetic regimes are difficult, because you can imagine that the concentration within the grain boundary area itself is small. Therefore, the concentration that has to be detected in order to get a sufficient statistically reliable data is extremely low, and that how do you detect using an appropriate technique is very challenging. So, usually radio tracer diffusion is the only way which allows you to do this kind of measurements in C kinetic regime, because it has a high nuclear counting sensitivity. So, you can detect a small amount of tracer concentration, but otherwise it is challenging to perform experiments in the C kinetic regime because of detection limits of the small amount of the diffusing atoms. Now, just a word on how do you determine the segregation factor. So, remember the segregation factor actually can be determined by simultaneous or by combined measurement in B and C kinetic regimes. So, you remember in the B kinetic regime what we measure is S delta into DGB, whereas in the type C regime we can directly measure DGB. So, if you combine these experiment, you can take the ratio of this, which gives you S into delta, and S into delta we know delta is approximately equal to 0.5 nanometers, and that way you can actually determine the segregation factor. So, this triple product is also follows an Arrhenius relation, and similarly S also is expressed as S naught into exponential delta H segregation by RT. You note the absence of minus sign here. It is not that it is a typing error, it is like that. It is an activity question for you to think why positive sign is here. Usually we are used to see whenever exponential by RT something is there, then there is a negative sign. But in this case there is a positive sign. Think about it, why this negative sign does not come into picture here. So, the DGB is also equal to DGB naught into exponential minus delta H GB by RT, and this Q for the grain boundary diffusion is the delta H grain boundary minus delta H segregation. The last couple of minutes, just I want to throw some insights on what is the atomic mechanisms of grain boundary diffusion. Now, inside the grain boundary, how do you think the atoms move? Is it vacancy or the interstitials or something else? So, usually because in the grain boundaries you do not have a periodic arrangement like a lattice. So, vacancy within a grain boundary is much easier to create than within the grain. So, you see that the grain boundary within the grain boundary vacancies can be created. But what it also means is that vacancy in grain boundary at a particular location can be different from the vacancy in the grain boundary at another location because of the surrounding atoms. In the lattice, surrounding atoms are similar everywhere, okay, but in the grain boundaries that may change. So, the variations from site to site within the grain boundaries can be significant. And the formation energies of vacancies and interstitials are close to each other, and therefore, both are important within the grain boundary. And depending on the grain boundary structure, the grain boundary diffusion can be either dominated by vacancies or by the interstitials. And you can have single jump and collective mechanisms both operative in the case of grain boundary diffusion. So, vacancies, because here they can, like by single atom jump exchanges, they as they do in lattice also can happen, but collective jumps are also possible, which involves simultaneous displacement of several atoms. And interstitials can move by direct or indirect mechanism, where in the direct mechanism they go along the grain boundary by jumping between the neighboring interstitial positions, whereas in the indirect mechanism they displace a neighboring regular atom and takes its place, and that atom is displaced from its original position. So, these are the some of the features of the atomic mechanisms of grain boundary diffusion, without going too much into detail. So, with this we will end the discussion on the grain boundary diffusion, and in the next class we will talk about another important diffusion path, which is the dislocations. So, thank you.